Welcome to the Astrobiology Colloquium. I'm Tim Elam. I'm substituting for David this afternoon while he's in New York. And he asked me to host Ken while he's here because I'm part of the Mars 2020 science team. So obviously I'm delighted to have Ken here. Ken Williford is the Deputy Project Scientist for the Mars 2020 project. He received his bachelor's degree at the University of the South in Sewanee, Tennessee, and then a master's from here at UW in geological sciences before it was the Earth and Space Science Department. He then went off for a few years teaching, and he tells me he went to film school during that time, but then eventually came back here to get his PhD in what was now the Earth and Space Sciences Department, and was also part of this astrobiology program. He worked under Peter Ward when he was here. He did postdocs at Curtin University in Perth, and at the University of Wisconsin-Madison, and then eventually took a permanent job at the Jet Propulsion Laboratory. And in 2013, he became the Deputy Project Scientist for Mars 2020. And Ken is going to tell us about the Mars 2020 Rover mission. Ken?
Thank you. Thanks, Tim. And thanks to all the folks who helped set this up. I have sat where you're sitting for many an astrobiology colloquium over the years. It's been a while. 12 years or so, 11 or 12 years. And I can't tell you what a pleasure, and really it's an honor to be back here, to be invited back here to come and share with you about what I'm up to these days at JPL, which is largely the Mars 2020 rover mission. I originally came to JPL before Mars 2020 existed as a mission. MSL had recently landed, the Curiosity rover had landed. JPL has been interested for quite a while in Mars sample return. I took a job as an organic geochemist to come set up a lab and work on Mars sample return. You know, I was very excited about that when I came to JPL, and I would tell people, I came here to work on Mars sample return. They would go, ha ha, you know, we're always a decade away from Mars sample return, and a lot of cynical comments like that, which we'll talk about a little bit more later. But so I did set up a lab, and so I run a lab. Still do my own science from time to time. We'll see a little bit of that, but most of what I'm going to talk to you about today is our work on Mars 2020, which is the next NASA mission to the surface of Mars. So, part one, Mars 2020. So this is what it looks like right here, right now, in what we call the SAF, the Spacecraft Assembly Facility at JPL, in Building 179. This is the largest clean room at JPL, and it is where every Mars rover has been assembled, along with many other flight projects that you'd be familiar with. You see all those badges up in the back wall of the room. That's all the spacecraft that have been built here. You can't read any of them. But there's a lot going on. Clearly, the technicians don't really move this fast at JPL. But the main thing you see there towards the center of the image is the spacecraft in what we call the stacked configuration. So it's rotating. The big black thing you see that was just on the top is the heat shield. So that would be entering from that in this, sorry, not this configuration. So with that black thing facing the Mars atmosphere. So that's what protects the spacecraft as it enters the Mars atmosphere. Then we have on top of that is the back shell, which protects the spacecraft, and then these sort of little curved rectangles, the circular curved rectangles that are above that is the cruise stage. So that's the spacecraft that cruises the whole thing to Mars, flies the whole thing to Mars. Packed up inside the back shell, when it turns over, you can see a rectangular box. That is where the rover would be. We call that the FOVR, or the surrogate rover. And the real rover actually appears up in the kind of near the top right corner. It's not there. I'll tell you when it appears. You look where I'm pointing. It is there now. So that's the real rover. And this process that you see going on here is called ATLO, Assembly Test Launch Operations. And this is all about assembling the spacecraft, putting all the subsystems together, and then the T is for testing. So we want to test all those systems, and having the surrogate rover inside the stacked configuration allows us to do lots of tests of the whole spacecraft stacked up without burdening the rover itself, which is you know, the source of a lot of complex testing needs. And so all kinds of stuff going on in that lab. And if we have time, towards the end, I've got a bunch of other pictures of spacecraft hardware that I can show you. So this is what we hope, this is of course an artist concept but what we hope the rover will look like sometime in 2021. It will not be sitting in this place, which is an image from MSL. We don't think we're going to Gale. We'll talk more about where we are going in a minute, but you'll notice it looks, those of you familiar who follow these rover missions will notice it looks very much like the MSL Curiosity rover, and that you are correct in that assessment. It was built, the mission from the very beginning, kind of baked into its DNA, is what we call a heritage approach. So the story that I've been told is that the flight system manager on MSL, so the flight system is all the spacecraft. That doesn't include the scientific instruments, basically. So the mission breaks down into the flight system, the payload system. The payload is all the scientific instruments, and then the mission system. That's the team who's responsible for running the mission on the surface, operations and so forth. So the flight system manager, the person who's in charge of managing the giant team who has to assemble all the parts and put them together and test the parts of the spacecraft, not including the payload. During the cruise phase of MSL, while the spacecraft was flying to Mars back in 2011, 2012, had a little bit less than the typical workload because the spacecraft is all assembled and flying to Mars. And he made the list of all the spare parts that were laying around and thought, hey, we could do another one of these for not as much money. And I'm not sure if this is exactly how it worked, but anyway, someone proposed an idea like that. Negotiations happened with NASA, and the concept arose to do another rover mission where the rover would be, as much as possible, a duplicate, build to print. That is, we would build to the design of MSL whenever possible, and use spare parts from MSL whenever possible, but have a new scientific payload and participate in Mars sample return. So that was announced coincidentally on the day I arrived at JPL. I got an email saying there is now a mission called Mars 2020. So what is this mission? Well, it starts with all the work we're doing now, but the real fun starts in July 2020 with the launch, and this is the launch of MSL. I wonder if anyone in this room was there. Did anyone go to the MSL launch? No, I know some people from this program were invited, but this was the MSL launch. We hope it looks just like this. It's on an Atlas V rocket, and our launch window opens on July 17th, 2020. Then we move into the cruise phase, where it takes us 7 months to get from Cape Canaveral to Mars. And we know our arrival date, it's February 18th, 2021. We're going to a place called Jezero Crater, at which point we go into the entry, descent, and landing phase. And here we do the crazy-looking sky crane maneuver that MSL demonstrated successfully back in 2012. Where the descent stage, I didn't talk about that in the Atlo photo, but there's actually another spacecraft in that stack configuration. That's the one you see here, flying with retro rockets above the rover, and it flies down. So a parachute opens, the back shell separates, the parachute gets cut, and then you come down on powered flight on this spacecraft called the descent stage with retro rockets firing. But you don't want to come all the way down to the surface on rockets, because that kicks up so much material that comes right back down on the sensitive instruments of the rover, and it overly contaminates the surface. So instead, the rover gets lowered on this bridle down as the descent stage is hovering above. And as soon as zero velocity is registered, so the tension on those bridles releases, the descent stage knows the rover's on the surface. Pyros fire, charges fire on the top deck of the rover and cut those cables. The descent stage flies away and crashes at a safe distance. And so that's our entry, descent, and landing process, at which point we begin the surface mission. And so we have a 1 Mars year, that's about 2 Earth year prime mission duration. So that is what we're currently funded to do. The rover, we hope and expect, can last much longer than that. And so if we do our job well, we hope that NASA sees fit to extend our mission. We've qualified the systems to 1.5 Mars years. The reason we did this, so we stretched out the system qualification beyond what MSL was qualified for, that is 1 Mars year, because we have a set of objectives that's actually significantly more ambitious than MSL had, but with the same prime mission duration. So what are those objectives? Well, it starts here, just as MSL started, with an objective to land in a new exploration environment, new to the mission, but generally probably very old rocks, so billions of years old, from rocks deposited early in Mars history, and understand the geology, understand the processes of formation and alteration that led to the rocks that we see around us. Next step is we move into the astrobiology portion. So this is something that really excites me. I've been interested in, I was telling Vicki in our conversation earlier, I have been interested in and part of the astrobiology community for quite a while now. I really feel like it's an incredible opportunity. We are literally, with this mission, for the first time, I would say, since Viking, we have a core objective to seek the signs of life on another planet. So we are really authentically doing astrobiology in a way that goes a bit beyond what previous missions have done. But we start by doing what MSL did. So understand the basic geology, evaluate the depositional environment for habitability. Could this environment have supported life? But then we take that next step and we actually seek evidence of past life. So look for what we call potential biosignatures. A big deal was made about whether we could find conclusive biosignatures or not. There are some examples of things we could observe on the surface of Mars that would be fairly conclusive evidence of life, but it's quite unlikely. Almost certainly anything we observe is potential, and that would have to be confirmed by getting samples back, which is our next objective. So is to collect samples. So as we explore our environment, we will identify locations that we think have the best chance of preserving signs of ancient life or environmental change, and we will collect samples. So Mars 2020, like the Curiosity rover, has a drill. The Curiosity drill made the first holes in another planet, drilled holes in another planet anyway, but it collects powder and delivers powder into instruments that are inside the body of the rover, the SAM and ChemMin instruments, very capable bulk geochemistry and mineralogy instruments. Our drill is different. It makes cores, and so our drill is out at the end of the robotic arm. There's a second robotic arm that's inside the body of the rover where those laboratory instruments are on the Curiosity rover. Inside the front of the rover, there's a little second robotic arm, the sample handling arm, inside what we call the adaptive caching assembly. So this is one of the most complex and challenging parts of the Mars 2020 development, is the sampling system. And inside there are tubes, 42 titanium sample tubes that are hyper clean. So cleanliness and contamination control and planetary protection that goes along with it are among our utmost concerns on this mission. So much attention has gone into keeping these tubes and these systems clean. Anyway, so they're in their super clean environment. There's seals that we want to eventually seal the tubes once they have a sample in. There's a little camera inside. We want to take pictures of the samples once we have them. So basically what happens is the robotic arm docks with another little robotic mechanism called the bit exchange, the bit carousel, docks with the front of the rover. We'll generally be carrying around a drill bit that's really an abrading bit. So it doesn't make cores, it's just sort of like a jackhammer that abrades a 45 millimeter diameter circle, flattens that into the rock for analysis by our spatially resolved instruments. So we would swap out the abrading bit for a coring bit. And into that coring bit, before we pull the robotic arm away, the sample handling arm will have inserted a clean, empty sample tube. And we retract that, drill into the surface of Mars, and the rock goes up into the clean sample tube. We redock again, sample handling arm takes that drill bit off that has the tube inside, extracts the tube, moves it over through different stations. So we have a volume probe to measure the volume of sample that's inside. We have a camera to take a picture of the top of the sample. And then we have a sealing station. So we press fit a seal in there to make a hermetic seal, protect the volatiles inside the sample. And then we stick the tube back in tube storage. We can store the tubes for as long as we like, and then at some later point in the mission, we drop the sample tubes in collections of samples that we call a depot. And so we could make one or more depots along the way. The original idea is we'd put them all in one container, and at the end of the sampling phase, we'd put that container on the surface of Mars. This was one of the most interesting parts of the mission for me. Is early on we struggled with this design because we understood that the more samples we put in that container, the higher the risk is, right? The more value you have stuck there in the rover. So we talked a lot about the dead rover scenario where we die, you know, up next to a cliff, say, where we've been taking samples, and we've got those precious samples in there, and if you want to do Mars sample return, you have to have a retrieval mission that can go and jaws of life its way inside the rover and pull out the samples or some other such thing. And so to avoid that and to offload the risk, we changed the design. And so we have the design where we drop individual tubes on the ground and allows us to be flexible. We can hold them all till the very end, or we can create different collections and sort of offload a whole bunch of risk all at once and move on. So sampling, went on a little tangent there, but last objective is to prepare for future human exploration. And so we're doing two things very specifically. Two of our instruments very specifically prepare for human exploration. That is MEDA, the weather station, contributed from Spain. They also contributed the REMS weather station on MSL. And then MOXIE, which is solid oxide electrolysis, little a chemical plant that converts CO2 into oxygen that astronauts could breathe or use to fuel their rocket to get home. And so that's really a technology demo. But in a more general sense, everything we do prepares us better everything we do on the surface of Mars prepares us better to get humans there and back safely. So what's our scientific exploration model? Just briefly, I'll read this paragraph to give you a sense of, concise sense of how we expect to operate. We will develop geologic context for ancient Martian environments using observations made at a range of spatial scales, culminating in a search for potential biosignatures. We'll use the emerging geologic and astrobiologic model to guide the collection of samples that maximize opportunities to understand Mars as a planetary system and determine whether it was once inhabited. So that's our mission in a nutshell. And how do we do it? We use these scientific instruments. So just put sort of some examples of kind of data products that would relate to the mission. So we'll land. The first thing we do, just like we're a real robotic geologist, just like a human geologist, you take a look around, look at the colors and textures and structures that you see around you, start to understand the basic geology. For that, we use Mastcam Z. The Z there, the Mastcam means there's cameras up on the mast. The Z means zoom. So we have two identical zoom lenses. We can do stereoscopic zoom imaging on Mars with Mastcam Z. We have a totally new technology for the surface of Mars, ground-penetrating radar contributed from Norway called RIMFAX that lives on the back of the rover. Its antenna does anyway. And as we rove around, RIMFAX will be looking into the subsurface for the first time from the surface of Mars. There's some ground-penetrating radar in orbit, but this is the first time on the surface. And so helping to correlate structures we see on the surface potentially with things we see in the subsurface. All the while we'll be using MEDA to measure weather, MOXIE to generate CO2 from oxygen, but then it starts to get really interesting from a mission geochemistry perspective. We can use SuperCam, which is the next evolution of an instrument on MSL, which is called ChemCam. There's a partnership between France and Los Alamos National Labs. And this is the instrument up on the remote sensing mass. It looks like a big eye, like a big cyclops eye. That's a telescope that has a laser in the middle. And so it has a telescopic imager called the remote micro imager. In the middle, there's a laser. And on MSL, it uses a technique called LIBS, laser-induced breakdown spectroscopy. You shoot at a rock from some meters away, generate a plasma, and use the telescope and a spectrometer to analyze the elemental composition of the rock that you're shooting. So you're doing remote geochemistry in that way. We have those capabilities on 2020 with SuperCam as well, but we add Raman spectroscopy and visible near-infrared spectroscopy to the suite. So we can do Raman at a distance, which is incredibly powerful, allows us to do mineralogy, and if there were very high concentrations of organic matter, we could potentially detect organics, but we'd have to be hitting something like a coal seam, which seems unlikely. Luckily, we have another instrument out on the turret called Sherlock. And so the next three you see here are Watson, Pixel, and Sherlock. Watson and Sherlock go together. They're two parts of the same instrument. Watson is a reflight of the MALI camera from MSL, the Mars Hand Lens Imager. This is like, imagine a macro imager, get up real close and almost like a hand lens for a geologist to see individual sedimentary grains. So its spatial resolution is basically set such that we can see down to the finest sand grain. So we can resolve mudstones from sandstones with this camera. Also, look for interesting morphologic biosignatures potentially. If we ran into something like a stromatolite, Watson would be able to see that. And so Watson, and that's the imaging part of Sherlock. Sherlock spectroscopy uses a deep UV laser, rasters that over the area about several square, or about a square centimeter. The beam itself is 100 microns in diameter. It rasters that beam across that area and uses fluorescence and Raman spectroscopy to map the mineralogic, really the molecular composition. So it does mineralogy and organic detection and organic classification. Pixel, similarly, over on the other side of the turret, so this is what Tim primarily works on. This is also has about 100 micron spot size, but in this case it's an X-ray beam. And it's rastering that micro-focused X-ray beam over a similar area and making a map of elemental composition. So what you get out of this is something like a micro XRF, if you're used to that, or what I use mostly is an SEM and EDS, and generate these kind of elemental maps. So a very basic product for geology, but totally new for Mars surface missions. So previously we've been able to use APXS to generate a bulk elemental composition over about a square centimeter, but the ability to map composition at the scale of individual sedimentary grains is totally new. The last thing you see here is RSS, that's return sample science. And so we will have a group of scientists, the call is actually out now, the proposals are being reviewed now, participating scientists who will come onto the mission who have specific expertise of the kind that would be required of scientists who could receive the samples that we're collecting, if that makes sense. So the kind of people who would be competing for access to Mars samples if they are successfully returned one day to analyze them in their lab. We're getting those types of folks onto the mission to help advocate for the interests of those scientists and help us understand the best type of samples to collect. So what do we mean by seeking signs of ancient life? So here you see an image of 3.4 billion year old stromatolite. It's from the Strelly Pool Formation. And so it says it's fossil microbial mat. So that's something we know from all the work we've done on it here on Earth. But what if we find something like this on Mars? So Mars 2020 can recognize potential biosignatures as, in general, lifelike patterns in the exploration environment. But more specifically, concentrations of biologically important elements, minerals, and or molecules, particularly when they are spatially associated with biologically suggestive morphologies. So that's how this payload is designed, and that's how the exploration strategy of 2020 is designed. When we're, the part of our mission that involves looking for signs of ancient life, that's what we mean. We're looking for shapes that are potentially indicative of biology, but it can't stop there. Just like on Earth, it can't stop there. Just like on the Allen Hills meteorite, it can't stop there. We can get confused if we rely solely on morphology, so we want to use spatially resolved geochemistry to look for lifelike patterns in the chemistry that align with lifelike patterns that are morphologic. So here you see some, wrinkly layers, so morphologic biosignature in the visible image. And then you use pixels, so the pixel breadboard or brass board, I don't remember, was used to make this map. So very similar instrument to the pixel flight model, mapping, in this case, silicon, calcium, and iron. And so what you see here is original carbonate, calcium and iron carbonate, that has been silicified, partially silicified. And you can see here that the silicon in green aligns with the dark layers in the visible image. Now we map it with Sherlock, and we see in red we have quartz, in blue we have dolomite. So we go from understanding that that's calcium and iron to knowing from Raman that that's actually the mineral dolomite with variable iron concentration. And then in green, correlated with the quartz there, And those dark bands in the visible image is kerogen. So clear detections of organic matter in a setting that is analogous to what we might hope to encounter at Mars someday. So part 2, Mars sample return. So I went searching for a past talk, I think for a meeting in Berlin last year on Mars sample return, for the oldest evidence I could find at JPL, official evidence I could find at JPL of a study relating to Mars sample return. There's information that studies were going on as far back as the late 60s, but the only one I could find actually in print was this one. It comes from 1984, so 35 years ago. And you see this architecture they have here. They've got an orbiter flying around Mars. They've got a little rover out there collecting samples. And they have a platform lander with a rocket on board. And you see a sort of ball-shaped object near the top of the rocket. I would imagine that is what we would now call the orbiting sample. This is from a couple years ago. Same architecture. So we had it figured out a long time ago in terms of basically how it should work. It's 3 missions. There's Mars 2020. Our job is to select and collect the samples, deposit them safely on the surface, and then if we're successful and if all the politics and the money works out, 2 additional missions would be funded to get our samples back. There's a study going on currently that would have those launching as early as 2026. You would simultaneously launch the next 2 missions, an orbiter and a lander. This would be a partnership between NASA and ESA. There's a lot that has to go right to even get this mission funded. But the idea is that potentially the Europeans would supply the orbiter. NASA would supply the payload for that orbiter, which is a rendezvous and capture system that would capture our samples in orbit. Europeans would provide the lander, the platform lander, and a small rover that would rove off that platform and fetch our samples that we leave on the surface of Mars. That's its only job. And to get them back safely to the lander, where it would put them in the MAV, the Mars Ascent Vehicle that NASA would provide and JPL probably would provide. So the idea is we collect the samples, you land on Mars, this other mission which has a lander, a rover, and a MAV. The little rover goes out, gets our samples, brings them back, puts them in the MAV, launch it inside actually this ball-shaped thing, which is the orbiting sample, or the Oz, launches that whole thing into orbit. The Oz separates from the MAV. All the while, the orbiter is watching this happen and doing relay communications for this, monitoring the launch of the MAV. It has to then rendezvous with the Oz, get into orbit with the Oz, and then the rendezvous capture thing grabs onto this orbiting sample, dumps it into an Earth entry vehicle, looks like kind of like the Stardust capsule that landed and the Genesis capsule that landed. That flies back to Earth. Actually, you jettison parts of that spacecraft that you don't need, and only the minimal stuff that you need flies back to Earth. The Earth entry vehicle comes into the atmosphere. Interestingly, probably without a parachute, just slams into maybe the Utah test range, and we go get the samples and take them to the lab. So I joked that people told me, we're always a decade away from our sample return, but I'm here to tell you, officially, we are now a decade away from Mars sample return. As you see it right there, signed by Thomas Zurbuchen. He's called the Associate Administrator for Science, the Science Mission Directorate. So all these missions, these big scientific missions for NASA, he's in charge of that whole part of NASA that runs those things. And then his counterpart for ESA, David Parker, I guess they're broken down with human and robotic exploration. But anyway, they're basically equivalent in their levels, NASA and ESA. They signed this joint statement during that Berlin meeting last year, committing NASA and ESA to this joint partnership study. They'll release the results of that at the end of this calendar year. And then, if things go well in this respect in the Congress of the United States, we get budget for this. And if ESA can set aside the funds for this, then we'll be off and running for Mars sample return. So why would we do this? Well, this is a controversial idea, but in my own opinion, I think Mars sample return, the thing I'm most excited about is how it potentially revolutionizes science. I mean, it's absolutely transformative. But I also think it's a technology demo for getting humans to Mars and getting them back safely. I think you don't want to, if you're NASA, you don't want to send humans to the surface of Mars and expect to get them back safely until you've sent robots to Mars and brought back a few rocks safely. But there are a lot of people in the human program who think, bah, we don't need Mars sample return, we'll do it on our own. But from a scientific perspective, it's some things like this. So this is a microscopic photograph taken through focal planes of the Gunflint Iron Formation. So about 2 billion-year-old rocks from Canada, where really the first good evidence of Precambrian life, at least in the form of actual body fossils, was found in the 50s. These are fossil bacteria. So the arrow that you see pointing there is pointing to about a 1 micron diameter filament, we think probably a cyanobacterial filament. And that brown stuff is organic matter, it's kerogen. And this is a tube, a long tube that has, it's hollow on the inside. That's part of how we know it's clearly a microbial fossil. It's very hard to come up with an abiotic mechanism to form a morphology like that out of organic matter. If you look in other places, sort of towards the top left of the screen or elsewhere, you'll see a bunch of other little shapes. Some of them are just kind of amorphous blobs of organic matter, which itself was biological at some point, but is not in the form of a cellular fossil. This long filament that you see is truly a fossil cell. So the rock it's preserved in is called Blackshirt. So this very, very fine-grained microcrystalline quartz that makes up this rock called chert. It's the same thing as flint. And almost all of our fossil bacteria that we know of on Earth are in this kind of lithology, chert. Now, we have not seen a chert on Mars. We have found silica on Mars, but it's generally amorphous silica or opal A. It's not this kind of rock, chert. It's a very, very hard rock, and even if we encountered it with Mars 2020, it would be very tough to drill. We would certainly try if we found a black chert. But this is some figures from a paper by Bill Schaaf and some others showing cellular preservation of a very similar type to what we know of, what we're familiar with in chert, but this time in gypsum, bottom nucleated gypsum. And we have seen tons of sulfate minerals on Mars. And so this is potentially more perspective in terms of actually finding microbial fossils on the surface of Mars. If we found such things, here are some other examples of microfossils in Blackshirt. But in order to really observe these things, they're microscopic. So you generally have to make a polished thin section. So you need and so far we don't have a rover that can make thin sections. It can make powder or it can make cores. You could imagine a payload that could make a thin section, and people have thought about it. But you really need to see these things in transmitted light to be able to observe things like this. So we need to get samples back to even have a chance of seeing anything like this. As unlikely as it may be that we would get lucky enough to bring something like this back, to find it and bring it back, we certainly would not have a chance of seeing it unless we got it back. But then, say you do find it, and you find some spheres of organic matter. On the case here on the left, it's a 50 micron diameter sphere, hollow on the inside, and on the right, it's 4 spheres together. It's hard to make much of this. I think, there would be people who would argue about this to no end, whether that's biological or not. This is where I show you a little taste of the things that I do that aren't directly involved with Mars 2020. But in this case, we took these, located these microfossils in the same sample. The rock is about 750 million years old, the Chichcan Formation. And we observed these microfossils about 7 millimeters apart in the same section. And we put them in an instrument called a SIMS, a secondary ion mass spectrometer, University of Wisconsin. And we shot them with each 3 times. And so the images that you see on the top there are backscattered electron images from an SEM, electron microscope. So you're seeing the surface of the chert there in the kind of main gray color. And then you can see in the image in the top left a circle there, and that's where that sphere intersects with the surface. And the darker gray is the organic matter, the kerogen, that's exposed at the surface of the sample. On the right, you should see 4 circles like that, and then on each panel, you see 3 pits. They're kind of oval-shaped, little diagonally oriented pits. And those pits were sputtered away by a beam of cesium ions focused to about 15 microns diameter, or I guess major axis there. And that sputters away, that beam of cesium ions sputters away all the material in that pit and ionizes it at the same time. So we're getting lots of silicon ions, oxygen ions, carbon ions from the organic matter. We're interested in the carbon ions. We're actually generating little carbon-12 ions, carbon-13 ions. What we really want to know is the ratio of carbon-13 to carbon-12, or delta C13, the stable carbon isotope ratio of this organic matter. And we did that. We hit each one 3 times. And we found, you take the average of each, and we find the one on the right is minus 22.5 per mil. The one on the left is minus 29 per mil. So going in, we thought maybe this organism on the left is an algae, a eukaryotic organism, just because it's bigger. And the one on the right, maybe that's cyanobacteria, just because they're 4 little small cells. And the isotopic offset we found is exactly what you'd expect if the one on the right is bacterial and the one on the left is eukaryotic. And so we were able to confirm that with geochemistry. So you go from just these sort of non-diagnostic morphologies, spheres and filaments, to having some real information about the metabolism of these organisms. Now this is the instrument that's required to make those measurements, so way bigger than anything we could fit on a rover. And of course, we have bigger instruments, right? So here's the synchrotron at Brookhaven. So we need to get these samples back. We want to get these samples back to have any chance of really having anything like a conclusive answer about whether Mars was ever inhabited. We need to bring our best analytical techniques to bear. So part 3, operations. This is really the fun part of the mission. We are now in the transitioning from development to operations. And we're starting to think about how are we actually going to work this vehicle on the surface of Mars. And we're in the strategic process right now. That's at the top level. But we have all these phases of operations down to tactical. I want to kind of blow through this last part to make sure we leave time for questions. But I'll take about 5 minutes to tell you a little bit about where we're landing. So what you see here is the MOLA Mars Orbital Laser Altimeter map of Mars, showing you the topography. These were our final 3 landing sites we had in consideration. We started out looking at about 40. It's a process of 4 years of many scientists getting together and debating, hundreds at a time of scientists getting together and debating about once a year where we should send this rover. Boiled it down to the top 3, Jezero Crater, Northeast Syrtis, and Columbia Hills. Columbia Hills is where Spirit went in Gusev Crater. But you notice Jezero and Northeast Syrtis are located quite close to each other on the western edge of this giant impact basin, one of the largest on Mars, Isidis Planitia. And we actually had other landing sites that fell out of contention. There were many landing sites in this region. Why? Well, this goes back at least as far as this paper by Bethany Ellman and others, I think part of her PhD work, where she showed detections of carbonates for the first time based on infrared spectroscopy. So they were lured into this area from omega detections of high concentrations of olivine, and carbonate can be a weathering product of olivine, and they used the CRISM instrument on Mars Reconnaissance Orbiter to find carbonates. And you see these were all concentrated around that western, or in some cases southern Isidis region, and on the right there you see nili fossae, these linear fractures going into the crust there, and a lot of carbonate detections. So why do we care so much about carbonate? Well, it has carbon in it, so it's automatically relevant to astrobiology. So it often on Earth is associated with life. It's a very common biomineral, or a class of biominerals. But in addition to that, so it can preserve biosignatures, but it also preserves records of the interaction of the atmosphere. Mars' atmosphere is rich in CO2 with surface water. And so we're interested in it from its ability to preserve climate records as well. But you see 3 major features here in our broad exploration region. The top right, Utopia Planitia. So if there was a northern ocean on Mars, controversial idea, if there was a northern ocean, it was here in this basin and potentially flowed into Isidis there. And you see the age of Isidis is estimated from crater counts at 3.96 billion years old. And then there's this giant volcanic province down in the southwest there, Syrtis Major. So there's giant impact basins. So the story of Jezero Crater goes back to the story of planet formation, truly. I mean, of the time when planetary embryos are crashing into each other and forming impact basins the size of Utopia Planitia. And Isidis is one of these very early giant impact basins. And so it's possible, we think, that pieces of the crust that the Isidis impactor struck were thrown up and formed Megabarcher that might be accessible to our exploration. So that's one of our major targets. On the western edge of Isidis, you see one of our potential landing sites, Northeast Syrtis. And what you find in Northeast Syrtis is not strong, solid evidence of flowing surface water or rivers or lakes or anything like that, but good, clear mineralogic evidence of aqueous alteration of what looks to be igneous crust, an extremely ancient, some of the oldest or the oldest crust exposed at the surface of Mars. And you have hydrous minerals there in association with those mafic or ultramafic lithologies in exposures like this. So you see these mesas where you get concentric emplacement of, you find the basement here, which is low calcium pyroxene and it's clay bearing, so it's been altered in the presence of water. And in some cases, there's Megabarcher, so giant 100, 200 meter size blocks of stuff thrown up by the Isidis impact and emplaced in the basement there. So that's obviously interesting. And then the next unit is this carbonate-bearing light-tone fractured unit, potentially an episode of strong aqueous alteration of that mafic or ultramafic crust. And then on top of that is a mafic capping unit with high calcium pyroxene. So potentially a record of the evolution of the Martian interior in that igneous stratigraphy. Here's just a taste of what Megabarcher looks like. You can't see the scale bars there, but they're either in the top left image, it's 100 meters, the whole scale bar, and in the one just to the right of that, it's 200 meters. These are giant blocks of crust thrown up and re-emplaced, planed off by erosion that we could go sample. And it would give us a record of the rocks that were there prior to the Isidis impact, so very early in Mars crust formation. So then we were debating, it was really down to Northeast Syrtis or Jezero. And Jezero, very different site. So 40-kilometer diameter crater on the western edge of Isidis, just north of that Northeast Syrtis landing site. And so the crater itself sits in that terrain that makes up Northeast Syrtis. So the same kind of geology we saw on the last slide, that's the geology that the Jezero impactor impacted, formed a crater. Into that crater flowed a river. You can see the channel there on the left side of the image, flowing into the crater wall and depositing this beautiful fan, a delta, which is very strong evidence to us that there was a standing body of water there into which that river flowed. So there was very clearly a lake inside Jezero Crater. An interesting and unique thing about Jezero relative to other crater lakes on Mars, there's also an outflow channel. So at least for some significant period, Jezero operated as an open system, so it was refreshing itself with new water from the outside and flowing in. So just some of the textures or geomorphology you see at Jezero. So backing up here, just at the edge of the fan, you see stratigraphy like this. So we're particularly interested in the beds towards the bottom of the delta, the fine-grained delta deposits that would have been further out in the basin, do a great job of preserving organic matter if organic matter was there. Think the shaly type rocks. On top of that are the coarse-grained delta deposits. Maybe not quite as good at preserving organic matter, but what these do for us is they concentrate the geologic diversity of the watershed. So all that Northeast Syrtis type terrain that the river was flowing over was breaking up those rocks, forming sand and delivering that sand to the top of the delta. Every single sand grain in that core of coarse-grained delta deposit that we bring back is its own individual little sample. You know, there's an incredible amount of work we could do on that type of rock. Then, one of the lithologies I'm most excited about are the carbonates in Jezero, and we have two types of carbonate exposures. You see the orange stuff down to the sort of the right side of the delta there. That's carbonate exposed down in the basin, but we also have carbonates exposed right on the margins of what would have been Jezero Lake. And so this is what I'm probably most excited about. We know if there was clearly a lake in Jezero, The lake must have been bounded by the crater rim. Therefore, the intersection of the clearly subaqueously deposited sediments in Jezero Crater and that crater rim were the margins of the lake. So there must be marginal facies exposed there. We know from infrared spectra that there are carbonates in those rocks. Now, what we don't know is if the carbonates are associated in time. Did they form at the same time as lake deposition was going on in Jezero? We don't know. That's one of the big science questions going in. But if they did, if, for instance, carbonates that were up in northeast Syrtis were eroded and or dissolved into that river system, and the river brought in alkalinity into the Jezero Lake, raised the alkalinity of the lake above saturation point for carbonates, and we had a situation where on the margins of a crater lake, there in shallow environments where microbial mats could easily form on substrates in an environment that supported calcification, that's an incredibly, has incredibly high potential for biosignature preservation. So I'm very excited to go and visit what we call the marginal carbonates. Here's what they look like in the high-rise images. So then lastly, at Jezero, we have this what we call the Mafic crater floor unit, and on the bottom right there you see underneath that unit are these basinal carbonate-bearing deposits, and then up at the top right, I'll flash back to this image, so you see those little knobs at the edge of the white rectangle there. Those are delta remnants. So we believe that the delta extended at least that far and has been eroded back, and it left little pieces of itself out there as delta remnants. You see up there at the top right. So there's old delta stratigraphy out there. There's Mafic crater floor. This may be a volcanic unit. If it is, that'd be great. We can get a sample of it. You can get a crater age, an age based on crater counting. That's how we get the age of almost everything in the solar system that is not the moon. And all of our crater counts are based on the lunar chronology, basically. So one of the big, part of the big scientific promise of Mars sample return is bringing back an in-place igneous rock from a unit that has a crater age to help tie in our crater chronology for Mars, the rest of Mars, and other bodies in the solar system. So the last piece here is our overall mission concept. So when we went to headquarters and we recommended the landing site that should be selected, so we don't make the decision. We actually take a recommendation to Thomas Verbuchen at headquarters, the guy who signed his name on the left of that paper. And he's the big decider. But what we recommended is that we land in Jezero, we spend the prime mission exploring the Jezero system, sampling all those units you just heard about, and getting ourselves up to the crater rim. There's fantastic stuff that can be done at the crater rim, including looking for impact-generated hydrothermal systems. So it's possible, if there was enough water in the crust at the time the Jezero impact occurred, it set up hydrothermal systems that flowed through that crater wall, through that crater rim. And so we could go looking for that sort of thing. That would have been a totally different kind of habitable environment than the lake. Could have, of course, exchanged organisms with the lake or who knows what. But we'd get up there, do a little bit of exploration of that, and that would be the end of our prime mission. If we're doing well, we're successful, the vehicle's healthy, and there's enough money, we could be granted an extended mission during which we would drive and do more exploration of the crater rim, then get outside of Jezero Crater and start exploring that northeast Syrtis type, extremely ancient crustal formation processes, planetary evolution type questions, potentially sample that Isidis Megabarcher, and then we located a safe landing site that has northeast Syrtis type geology within it, but where a return mission could land safely if it had the same landing capabilities of Mars 2020. So that's what we recommended. What was announced was we're going to Jezero Crater. But since I came here to talk to you about what we hope to do with the mission, this is right now what we hope to do. So we believe this would take us about 6 years or so to get that whole mission done, and that would put us in a good place if Mars sample return follow-on missions launch in 2026 to actually be there to potentially deliver some samples to that rover. So I'm going to end it there to make sure we have some time for questions, but thanks a lot. Peter.
Ken, I was struck by how similar to the Theranos Edison machine you guys are building. They have the blood sampling
Yeah, well, our tubes are much bigger than the Theranos tubes. So, and I believe we probably have many, many more engineers working on them, my guess is, than the Theranos tubes. What's that? Yeah. We have engineers working on them. No, I mean, it's a good question. It is maybe the biggest challenge that we have is to get the sampling system to work. But it's what JPL does. It takes on things that seem impossible and often makes them possible. So, I mean, the answer is, you know, very hard work, a lot of iterative design, a lot of reviews with young people and senior people who've seen it all before, and correcting mistakes, and then testing, test as you fly is the mantra at JPL, and that's what's going on now, a lot of testing. But so far, it's working quite well. The trick is to have it keep working on Mars where we can't go and repair it if it breaks. Yep.
It seems like there's a lot more instrumentation on this than there was on Curiosity.
Hmm.
It seems like just a whole lot more. And it also looks like a typical, like sample gathering, tubes and everything else. But this lander must be a lot heavier.
It is slightly heavier. Yeah, there's actually not that much more instrumentation. So MSL had two big instruments that we don't have inside the body of the rover. So instead of those, we have the sample handling system. So that's sort of an even trade in terms of complexity. Ours is probably a bit more massive. But the instruments out on the turret are bigger. So our turret is definitely bigger, and it looks a little crazy to people familiar with Curiosity. They're bigger, but they're far more capable than what's on MSL. So it is, but we're using the same exact entry, descent, and landing. Well, the same from the perspective of mass. We have the same capability from the perspective of mass. We actually have some improvements over MSL. MSL could not have landed in Jezero. We have some hazard avoidance technology called terrain relative navigation that allows us to navigate relative to an image, an onboard image of the landing site. But in terms of mass, we're very close, about a ton. Yep. Yeah.
Yeah, what does the watershed for the Jezero fan look like? And say you do find something really interesting in one of those deposits, can you kind of back out the context from what you need?
To some extent, you can back it out, yeah. You're looking at it. You're looking at the watershed right now. So, yeah, so it's kind of dimmed to control the contrast there, but what you're seeing here is, I'll use the pointer. So you're seeing the rim of Jezero Crater right here, and the Jezero fan right there. This is the river channel. So all out here, all this terrain out here is what the river is sampling. And this geology all through here is roughly the same as far as we can tell from orbital images as Northeast Syrtis. We have very good infrared spectroscopy of the Northeast Syrtis landing site itself. We don't have the best kind of infrared spectroscopy that our capabilities allow up here, but you can correlate the units based on their geomorphology in Northeast Syrtis, and there's no reason to expect it should be dramatically different up here. But it's basically that kind of early Noachian igneous crust. Yeah. Yes.
I'm curious to know a little bit more about the ground-penetrating radar instrument that's
Mm-hmm.
going to be on the rover. So I know from some experience that you can kind of identify morphologies in the subsurface that might be indicative of like liquid material presence or other kinds of boundaries. So do you think this instrument has the resolution that you could identify any subsurface brine or liquid system if it's there?
Yes, it does. We do have that capability. It's certainly tens of meters. Originally, the thought was 100 meters maximum. Now, people talk about it in terms of tens of meters. So, I'm guessing maybe 50 meters, and the resolution decreases with depth. But we do have that capability.
Yeah. Do you think that's something that might be, come out from this
Yeah. It could be, it would be on the deeper end of that 50 meters, I would suspect. We don't expect there to be anything within, say, 5 or 10 meters of the surface. That's part of our criteria on selecting a landing site. We cannot go to a place where there's evidence of liquid water within 5 meters of the surface. Those places are called special regions, and in order to go there, you have to take special precautions that are especially expensive. And so we're not doing that. But you know, 20, 30, 40 meters, I don't really know. Maybe someone in the room knows, but I know at higher latitudes there is ice, you know, at the surface and at some latitudes, but subsurface ice and potentially liquid water. But I don't know at these more equatorial latitudes if there's anything that's been observed. I don't think so. Yeah. Yes?
So you're talking about like maybe going to the secondary site, the MDW, and having the like later rockets go there to pick up the samples that you deposit. If you aren't able to actually get that extension, is there still going to be some plan for returning samples from just the...
Absolutely. Yeah. So one of the things we've talked about is leaving a preliminary cache of samples in here. So what we might do in expectation of wanting to do this and taking this big risk, doing this big risky maneuver of going across the crater rim where everyone's going to freak out, we might double sample the most interesting targets, the say 7 to 10 most interesting targets that we encounter in Jezero. To some extent, we'll have to decide that strategically. But imagine double sampling 7 to 10. We then drop 7 to 10, for which we have duplicates on board, and we get out here. So the model for how many samples you could bring back has for a long time now been 31, and I won't get into why this weird 31 number has to do with close packing in a circle and so forth, and balancing the total mass that you want and how big each sample should be to get the science you want on each sample and so forth. All that gives you 31. So if we're going to get 31 samples back, we have 42 tubes on board, so we can afford to oversample by at least 11 or drop at least 11 and never bring them home and still get the full 31. So that's one thing we've talked about. And then of course, you know, if we get here and all signs point to no extended mission or whatever, you know, the rover health is not good enough to leave the crater, then we'd probably turn north and explore this stuff up here, because there's another fan, an older fan up here that you can see up here. It's more degraded. So we go and look at that stuff, but maybe just leave all our samples in Jezero.
Any more questions? The same thing.
Yes.
Oh, I'm sorry,
One more. Yes, that's not a silly question. What do I want to call the rover? Yeah. No comment. Actually, no comment should be the name of the rover. No, we are going to have that competition. It's been a matter of great consternation over the years. I mean, it was supposed to happen years ago, and then we had new administration and blah, blah, blah. But that should come out, I think, in the fall. So it'll run sort of for the fall semester, and school kids will, you know, K through 12, so you don't get to compete. Neither do I. So, but K through 12 will put their names in, and yeah, we'll choose one. The one thing Tim asked me about before this, and I didn't talk about, but one of the most exciting things to a lot of people is this helicopter that you see in front of you. This is the flight model of the Mars helicopter. So this, for the first time, if successful, will be the first whatever you call it, rotor vehicle or some technical word for it, but helicopter type thing flown on another planet. This is the one that will go. And so it'll be folded up, tucked underneath our belly pan. And one of the first things we'll do after we check out our basic systems is find a safe place to drop this thing off, and then we'll move about 50 meters away and we'll sit there for about a month while they demonstrate the technology of, first of all, flying up a meter and landing, and flying up a meter and going forward a meter and coming back and landing. And then 5 of these, with the idea being that eventually, so obviously humans going to Mars, it'd be fantastic to have drones to fly around and take pictures. But also future rover missions. I was talking to several people up there. This would massively improve our drive distance. If we had something that could fly out hundreds of meters and autonomously find its own landing site, this can't do that. It relies on us to find a landing site. But if it could do that drive, transmit the images and the digital elevation model of that 100 meters of 400 meters of terrain back to us, and we could plan a much faster drive. We would quadruple our driving speed by doing that. So that's the idea for the future of these things.
And the big deal is not the name of the rover, but the name of the helicopter.
Right. Well, it did have a name for a while, Leonardo, but I don't know if they'll keep that name. Yeah. Yeah.
Let's thank Ken one more time.
Thank you so much.